What's 3.8 and 3.10 about? Yeah, I mean, functions and, what's the other word also? Relations. What's the difference between a function and a relation? What's the difference between a function and a relation? There's one key difference between them. Sabine?
The function, you can't have 2 points that when you do a straight line does the straight line has 2 points. And a function.
Yeah, a function, for each input, there's only one output, which is what Sabine is mentioning graphically. So remember that a relation is any mapping of coordinates. So for example, 2, 3, 3, 7, 2, 5, 4, 8. This would be an example of a relation, these 4 coordinates. Or maybe they're written in a mapping form, where they're mapped from one to the other. And mapping this would look like this. It'd be 2, 3, 4, and the 2 would go to both 3 and 5. 3 would map to 7, and 4 would map to 8. And that's what the mapping would look like. And these are examples of, or this is an example of a relation. Why isn't this a function, though, this example specifically? What makes this not a function, Paul?
There's 2 2's.
Yeah, the input of 2 repeats itself. 2, 3 and 2, 5. Or if we look at the mapping diagram over here, whenever we see a branching off from here to here, we know that it's not a function. Because this input now has more than one output. Or it has multiple outputs. And we can see that graphically, as Sabine had mentioned, if we take a look at the graph of this. So I'm going to estimate these points, right? So 2, 3, maybe is there. 2, 5 is here. Then 3, 7, and then 4, 8. All right, that would be the 4 points I'd graph. I'm completely estimating. But I would see, obviously, that if I put a vertical line right here, it would fail the vertical line test. It would fail the vertical line test because this coordinate here and this coordinate here, okay, both pass, or the vertical line passes through both of those coordinates. Therefore, it's not a function. So the input of 2 has multiple outputs. That's why it's not an example of a function. Okay, you could have 2 different inputs with the same output. That's completely fine. Okay, so for example, if you didn't have that, if you had something like this, say you had, bless you, 3, 7, 4, 7, 2, 8, and 1, -5. This is a function. Okay, although you see that there's repeated outputs, that's fine. You can have repeated outputs. In pre-calculus, you'll learn, actually, I might get into it this year. I forget if I do or not. But in pre-calc, you'll definitely learn about inverses of functions. And you'll see that this has to do with the inverse of this function not being a function itself. But if you were to plot this to see, okay, 3, 7 would be like here, 4, 7, 2, 8, and then 1, -5 would be here. This clearly passes the vertical line test for all of these. Oops, I don't want the arrow, I want this line. Okay, it does pass the vertical line test. So this is here, here, and here. What would this fail? What kind of a test? Paul? Yeah, it would fail a horizontal line test, but we haven't learned about that. That's the test to see if the inverse of something is a function. Okay, the inverse, but I haven't studied that yet, so don't worry too much. But again, notice that you can have repeated outputs. You can have repeated outputs for a function to exist. For linear functions specifically, for linear functions, section 3.9, okay, the only difference we looked at was this. Instead of saying y equals mx plus b, it was f of x equals mx plus b. Where f of x is really just your dependent variable y. It's whatever's on the vertical axis. X is on the horizontal axis, that's your independent variable. M is still the slope, and b is still the y-intercept. Now, when we look at word problems, because that's where this is definitely going to come into play. I'll tell you right now, you have a word problem with linear functions for sure. When we look at word problems, what does b represent? Don't tell me y-intercept, because I know that already. But in word problems, in the context of a word problem. What is it, Brendan?
There's a starting point.
Yeah, the starting point or the starting value. Very good. So if I told you that this week, all right, gasoline was priced at $3.50 a gallon, but it was increasing and it was able to be predicted by some oil syndicate. It was able to be predicted that every day it increased by 15 cents. All right? $3.50 a gallon today. Every day it's going to go up by 15 cents for the next 5 days. What could you tell me about that function? What does that function look like? How could you describe that mathematically? What would it be? Will, follow it up.
F of x is 0.15 plus 350.
Plus, second? 350, very good. Okay, 0.15, don't forget your x, Will, okay? X. So 0.15x plus 350. What's the 0.15? What does the 0.15 come from in this problem?
It's a slope.
Yeah, it's the slope. And slope, mathematically, is defined as a rate of change. And use common sense now. The gasoline price is changing, right? 15 cents per day. That's a rate. Whenever you hear per, that is a rate. Now let's just, like 35 feet per second. That's a velocity, which is a rate. Or 25 cubic, or 25 gallons per minute. That's a volumetric flow rate of how fast fluid would flow. So when we're looking at a rate, that's what goes in for M, a rate of change. This is a starting value. Again, rate of change, starting value. We did an example, if you recall, with a gasoline or a tank losing fluid over time, where you're given 2 instances in time. Let's take a look at another example like that now. All right, let's say the following. Increasing instead of decreasing now. So we'll end up with a positive slope because we're going to say it's increasing. Give me something that can change as a function of time. What's something that can change as a function of time? Come up with an example. Who can think of something? What changes as a function of time? Stock prices. Perfect. All right. So let's say the following. Ready? Let's say that today the price of a stock is $21. Today the price of a stock is $21. Let's say that, and unfortunately stocks don't change in linear fashion, or else we could predict them, but assuming it changes in linear function. So today's stock price is $20, and on Friday the price will get up to $23.50. All right, so today the price of a stock is $21. Well, let's say last Friday actually instead of this Friday, because it makes sense because we would know it, right? We can't really predict. And then last Friday the price of the stock was $23.50. So this is going to be a decreasing actually in the end, which is fine. And we are to predict if this rate of change is constant, what the price of the stock will be this Thursday. All right, assuming a constant rate of change, which is not true really with stocks, but it does change as a function of time. Assuming a constant rate of change, what will the price of the stock be this Thursday? What might you call today as number of days? What might you call today?
Zero.
The 0 day, or the first day, or the second day, or whatever you want to call it, but I would choose 0, but it doesn't matter. You could call today day 2, and then last Friday we'd have to go back and figure out what day that is. But if you call today 0 day, all right, well on day 0, the price of the stock was $21. What would last Friday be then? Today's Monday and it's day 0. So yesterday would be day -1, Saturday would be, Friday would be. So on -3 day, okay, on 3 days ago, the price of the stock was 23.5. So that's how I start this problem. Remember, you have to take the context of the problem and write your coordinates first. When you have 2 coordinates, what can you always find? When you have 2 coordinates, you can always find the slope. So start by finding the slope. Slope is change in y over change in x. So if I'm finding the slope, I can say 23.5 minus 21 over -3 minus 0. Okay, again, I take my change in y over my change in x, and I'm consistent with the way I write it. So this change is 2.5, this change is negative 3. Which, if I were to double both of these, I get 5 over 6. Okay, instead of reducing and simplifying by dividing by something, multiply top and bottom by 2, you'll get integer values for your slope. Negative 5/6. Why is it negative? What's the significance of the negative in front of the slope? What's the significance, Ben?
Because it's decreasing over time.
Yes, the value of the stock is decreasing as a function of time. Okay, it went from $23.50 to $21. So it's got to be a negative slope because the function itself is decreasing. These are good words to use, Ben. Those are good words. It's decreasing over time. A function itself is falling or decreasing when its slope is negative. You're going to see this again in pre-calc and in AP Calc, the words, the terminology. All right, so we've got a slope. What else do we need to describe a line? We've got a slope and a y-intercept. Well, what's the y-intercept? Charles?
0, 21.
Yeah, it's given. There's no need to actually determine it. Whenever x equals 0, that's the y-intercept, right? Remember, to find the y-intercept, set x equal to 0. Well, you already did that. When x is 0, y is 21. That is your y-intercept. Now, if you didn't remember that, here's what you do. You write f of x equals negative 5/6 x plus b. And then you take one of the points, and you plug one of those points in. So 0, 21. Say you plug that in. You would get 21 here. Well, this is just going to be times 0, which is 0. So as a result, since this drops off, right, that part is just 0. Anything times 0 is 0. You get b equals 21, which is what Charles mentioned a moment ago. So since b is equal to 21, we can write our linear function as f of x equals negative 5/6 x plus 21. So this is the starting value of the stock, if today is the starting day, right? This is the change in the price of the stock as a function of time. Okay, and what would the units of 5/6 be? Anybody know what the units would be? Think about what's happening. Use the context of the problem to answer. What's happening in this problem? The stock is losing.
It's a decrease per day.
Decreasing what units though? What are the units?
Money.
What are the units of money? Dollars. Dollars per day. Here, this is what this physically tells me. This portion right here tells me that it's losing $5 in value of stock every 6 days. Dollars per day. Dollars per day times the amount of days plus $21, the starting value of the stock today. But when do we want to find the value of the stock? When are we trying to find the value? On Thursday. What's Thursday? What's Thursday relative to today? Today is day 0, Ryan? Why day 3?
Because Tuesday would be day 1, Wednesday 2, and then Thursday 3.
Yeah, if today is Monday and it's day 0, tomorrow's day 1, Wednesday's day 2, and Thursday's day 3. So we are now looking at day 3, not day negative 3 as earlier. Okay, so now we want to figure out what is the price of the stock 3 days into this trend. So we say, all right, well, what is f of 3? This is where function evaluation comes into play. When we did this, we evaluate a function. So we evaluate this when x is equal to 3. Please make life easier on yourself. Okay, when multiplying this, notice that the 3 and the 6 can reduce. Okay, so make this just simply a 2 in the bottom here. All right, so negative 5 over 2 is negative 2.5 plus 21, which is going to be equal to 18.5. So the price of the stock this Thursday is going to go down by $2.50. Okay, $2.50 because 3 days went by. And that makes sense. Use logic to always check. Go back, look here again. Remember what we said? This told us that the stock loses $5 every 6 days, right? Look at the slope. The slope says $5 of the stock value is lost every 6 days. Well, 3 days went by. So instead of losing $5, it lost half of that because 6 days didn't go by, but half of that went by. So it loses $2.50 every 3 days. All right? So we can see how the value of the stock decreases as a function of time. Do these problems make sense? The idea behind them? Linear functions are really important, and I mentioned this at the beginning of the chapter. I made sure to say, or to let you guys know that a lot of things in everyday life occur as linear functions. All right? Some things obviously change with parabolic behavior, which is like a quadratic function, or exponential growth. That's another big one. But linear is probably your most occurring that you're going to see. Let's quickly look at function evaluation and compositions. What section this was from? It was either 3.8, 3.9, or 3.10. But if you had something like the following. F of x equals 2x plus 1. G of x equals 3x squared minus 5. And I asked you to find the following. What is f of 2? What is that asking you to do? It says find f of 2. Well,
Plugging 2 for x.
yeah, plugging 2 for x. What do you got?
5.
5. Okay? Again, when you're asked to find the value of a function, it's like saying find a y value. The word value of the function or height of a function is synonymous with the y coordinate. Okay? The y coordinate. What you're plugging in here is the x coordinate, the location, the width of the function. So that's a simple example, obviously. What about g of negative 3? G of negative 3. And I purposely chose a negative number. And there's a squared with a coefficient, so be careful. There's a lot of room for simple mistakes in this kind of a problem. It's not a difficult problem, but there's a lot of room for simple mistakes. So I start by rewriting it. Okay, I start by rewriting it like that. Please remember that you're squaring negative 3. You're not squaring this entire thing. Don't multiply first. Remember PEMDAS, okay? Right, what do you got? 22. Okay, give me 27. This is going to be 9. It's still a 3. 27 minus 5, which is 22. So far, so good? How about compositions of functions? How about compositions? What about something like this? What about, and I'll put it on the top right, f of g of 2. What does that ask me to do? F of g of 2. How do you work this problem out? There's a certain way you want to do it, Ben?
First we find g of 2, and then you plug it into f.
Exactly right, Ben. So g of 2. Do g of 2 first, Ben. What do you got for g of 2?
Do the 7.
Good. 2 squared is 4. 4 times 3 is 12. Right? Do the 2 squared first, then that. 12 minus 5 is 7. So this is really telling us, as Ben said, to do that first. And g of 2 is really 7. So we replace the expression g of 2 that's on the inside there with 7. And then, to give you?
15.
Good. Okay, then this 7 goes into f right there. You give us 2 times 7 is 14. 14 plus 1 gives us the 15. Now, if you do a composition such as f of g of 2, and then a composition such as g of f of 2, you don't want to assume you're going to get the same answer. You can. You actually can get the same answer, but most of the time you're not going to get the same answer. So don't make that assumption that g of f of 2 and f of g of 2 are the exact same thing. What about something like this? Let's challenge us a little bit. I think you saw this in one of your problem set questions. So keep g in the back of your mind. Okay, the function for g. Let's take a look at this. What if we had g of m plus 1? How about that, where m is a constant, right? M is some constant number. How would I figure out what g of m plus 1 is? And I want it simplified, obviously. But what would I do to figure out what g of m plus 1 actually is? What do you got, Luca?
In the function of you take the begin, you take the slope.
Okay, so m is just a variable. M is a constant. It's not a slope here. M is just some constant. So what could I do with this quantity right here? Just what? Okay, so tell me, what would it look like?
So 3 times parentheses m plus 1
Good.
squared, that would minus 5.
Good.
And then you simplify it to m squared plus 1.
Be careful. Remember, we just went over multiplying. You got to write it like this. You got to think about it like that. You can't just distribute the square, right? Remember that?
M squared plus 2m
Plus
plus 2.
1.
Minus 5. Distribute 3. So 3m squared plus 6m squared minus 5. Maybe this final terms.
Which is just the last two, right? All right, so when you're evaluating a function, or you have a binomial, such as m plus 1, or 2n minus 5, or 3a plus 2, something like that, you need to remember that you're doing it the exact same way as if it had been a number. Okay? You're still plugging it in wherever you saw an x. So we saw it was 3x squared minus 5, and instead of an x there, we plug in the quantity m plus 1. And then we remember that you cannot distribute a square to a binomial. When a binomial is squared, you have to think of it as FOIL, or double distributive. And then go ahead and simplify further. Does that make sense, that example? Do you understand why? Anybody have a question on that kind of an example? You should definitely be able to do that. Okay, something where you have to evaluate an expression that goes into a function itself. What was 4.1 and 4.2 about? What was 4.1 and 4.2 about? Yeah, right.
Polynomial laws of exponents.
Yeah, good. Laws of exponents, terminology with polynomials. So let's take a look at some examples of those. You had some rules, and the rules are very important. If you struggle with the rules, what's your go-to solution? To mention this in class. For example, let's say this is the problem, right? Let's say it's this. And you forget what to do. Hypothetically, what could you do? Write it out. When in doubt, write it out. That completely just happened to rhyme. But when in doubt, just write it out like this. Now, take a look. Remember, multiplication is commutative. So I could put the 3 and the 5 together in the front. And then all the x's afterward. So when in doubt, just write it out. But you should remember these rules. And the solution to this will give you the rule. This becomes 15, x to the 7th. So what's the rule to go from here to here? To skip those intermediate steps. What's the rule that you remember? And make a full statement. When doing this, do the following. Louder.
When multiplying monomials, multiply like terms.
When multiplying monomials, I wouldn't say multiply like terms. I want to be more explicit with the rule.
Add the exponents.
Add the exponents. When multiplying monomials with the same base, we should specify, because if they're monomials such as x squared times y to the third, you can't just add the 2 and the 3 together anymore. So when multiplying monomials with the same base, add the exponents. Add the exponents. 2 plus 5 gives you this 7. And then the 3 times the 5 is obviously 15. Other rules. What's another rule? What's another one you remember? Go for it.
And that if two exponents are being multiplied on the opposite sides, in parentheses, and multiply.
Good. So if we had like 2x to the 4th to the 5th, this combines two of the rules actually. What Will told us was multiplication, so we're going to see that. How would I start this one? What would I do with the 5th power? It's like doing something else that we've done. We don't want to really call it this word, but it is kind of the same thing.
Multiply by 1.
So what does that part become?
2x. Oh, that part becomes
Okay.
And then.
What's the 2 become though? What's 2 to the 5th,
All
Paul?
I did was
What's 2 to the 5th? 32. So the key is to remember that although this is not mathematically correct to say it, it's like you're distributing this to both of these. This is really 2 to the 5th times x to the 4th to the 5th. Okay, that's really what's happening there. Remember that when you have a product raised to a power, you raise both of those factors, 2 and x to the 4th, to that power, which is a 5. And then, as Will stated, when you have a power to a power, you multiply those powers. That's what gives you the 20. And if you forgot that, remember this is really x4, x to the 4th, x to the 4th, x to the 4th, x to the 4th, which is really x to the 20th. Okay, so a power to a power, you multiply those powers. A power of a product, you distribute that power to both. You distribute that power. There was one more, I think. One more.
If there's a variable to the 0 power, it equals 1.
Yeah, anything to the 0 power except for 0 equals 1. Okay, any real number to the 0 power except for 0 itself, because that becomes 0, equals 1. All right, and that simply stated looks like this. Okay, a to the 0 equals 1. Some terminology you should definitely know. Whether it's asked directly or you have to use these words on the test. Some terminology, let's go through. How would you define something that's like a coefficient? What's a coefficient to you? How would you define that?
The number that comes before the variable.
Yeah, the numerical part of a monomial, or the number right before the variable. Good. What about a constant? What's a constant? What's a constant?
Like the numbers in the equation?
Yeah, just the number itself, not the variable part of the monomial. Okay. Most of the time, constants you use them by, you talk about them by themselves. Like if you had a function like 2x plus 7, 7 would be the constant. But technically, 2 is also a constant coefficient. All right? Does that make sense? Okay, so a constant is really the number part. A coefficient is the number part in front of the variable. What about monomial, binomial, polynomial? What do those mean?
Monomial is one
Sure.
term, yeah.
Okay.
Binomial is 2, trinomial is 3.
Yeah, and then poly is,
Or more.
yeah, there's many. So anything 2 or more, binomial is 2, trinomial is 3, and polynomial kind of stands for anything above 1. Other terms I'm trying to think about. Like terms. What do you know about like terms? They have to have the same what? It's very specific. Like terms have the same fill in the blank. Variable. Okay, variable part of the term. So like 2x to the third and 7x to the third are like terms because they're both x to the third. But 2x squared and 7x to the third are not like terms. Think about anything else that you should have a vocab. No, it's not vocab. Hey, let's take a look at domain. Let's take a look at domain now. So we looked at 2 types of domain problems. First type, which is a radical part. So let's say f of x equals the square root of 2x minus 7. And you were asked to figure out what is the domain of this function. First of all, what does domain mean? What does domain mean? What do you got, Sabine? Yeah, the x values. The values that x can take on. All right? So how would I figure out the domain for a problem like this? Why is there some sort of a limitation to the domain, first of all? Why is there a limitation? Luca?
Because it's the square root of it's under
Okay.
so it can't be less than 0.
Good. It cannot be less than 0. So it can be 0 or anything greater than 0. So what statement can I make? What statement can I write down, Paul?
Any real number, or not real number, positive.
Okay, this quantity, right, can be any positive or 0 number. So what can I write? Write it as an inequality, Paul. I could say it's what?
Greater than or equal to 0.
Very good, Paul. Well done. Greater than or equal to 0. Okay? Again, if it can be any number, 0 or positive, it's greater than or equal to 0. And then you just solve. And that will give you the domain every time. Again, whenever you have a radical function that's like this, not in the denominator. A radical function like this, just add the 7 over now, and then divide by 2. So that is your restricted domain. X must be greater than or equal to 3.5. Okay? X must be greater than or equal to 3.5. What about when you have a denominator? What's the difference? What if you have a denominator by itself? Like g of x equals 7 over x plus 1. Luca?
Just can't equal 0.
Yeah, the denominator cannot equal 0. All right, so x plus 1 cannot equal 0. Therefore, x cannot equal negative 1. That's your restricted domain. So it's all real numbers except for negative 1. Hey, remember for the first problem, if you want to write that in interval notation, the first problem, greater than or equal to 3.5 means from 3.5 all the way to infinity, including 3.5. So I could put a bracket there. So I could use set notation or interval notation for that. Either one is fine. Okay? Either one is fine. For this bottom one, I would probably write this, like this, and then say, okay, or you could even just say x cannot equal negative 1. You actually don't even need the XER part. We're assuming we're in the real number set anyway. What if you have a radical in the denominator? What if you have a radical in the denominator now?
It can't be 0 or negative.
Yeah, it can't be 0 or negative, so you say it's what? What does the inequality look like?
Greater than 0.
Greater than 0. So take a look up here real quick. If this had been in the denominator, the radical expression, this little equal to sign would not be here. And this would be a parenthesis instead. Okay, so the exact same problem. So say you had 1 over radical 2x minus 7. It's the same as the first problem we did, except now this is in the denominator. Okay? What about if you have something like this? How about this? It's not really much more difficult, it's just more involved. What would the domain restriction be in this kind of a problem? Good. X can definitely not equal negative 1 because it would make this factor 0, right? And then what's the other one, Charles? 1.5. Very good. How does Charles know that? He says, well, 2x minus 3 can equal 0. X plus 1 can equal 0. Okay, think of it as like a t-chart. Split it up. And then solve. Solving this one, you get negative 1. Solving this one, you can add 3. And then divide by 2, you get 1.5. So x cannot equal negative 1, and x cannot equal 1.5. There's two restrictions because there are two factors in the denominator. There are two factors in the denominator. What if this had just been x instead of x plus 1? What if I wrote it just like this? X times 2x minus 3. What's the restriction then? So instead of x plus 1, it's now just x times the quantity 2x minus 3. And, sorry, make believe the top doesn't have an x in it, because that would kind of throw this off, actually. Well, it really wouldn't, actually. It would still work, but for now. We'll get to that later.
Same, but in the lower x, cannot equal negative 1,
X cannot equal
0.
0. Very good. Remember, in the end, what you're doing is you're getting rid of this positive 1 here. you're setting each factor not equal to 0. Well, setting x not equal to 0 simply says x can't be 0. Because if x were 0, 0 times anything is still 0. So x can't be 0 now, and x can't be 1.5 now. All right, whenever you can factor out an x in a denominator, remember that x can't be 0 as a result. Because if you have x in the denominator factored out front, if you just put in a 0 there, the whole denominator becomes 0 automatically. There's no work to really do for that kind of a problem. There's much more. The last thing is section 4.3, which is what we just did. Section 4.3 is multiplying. Multiplying and adding and subtracting, so operations with polynomials. So when you have adding and subtracting, what's the one rule to remember, or what's the thing you want to remember? When you're adding and subtracting polynomials, just what? Fill in the blank. When adding or subtracting polynomials,
Combine like terms.
just combine like terms. Okay, so if you had something like this, let's do a subtraction one to make it a little harder. All right, something like that. I would begin this one, Mike. Yep. Just make that a positive and make these both negatives. All right, now technically speaking, I don't need this positive here anymore because I've got the negative there now. And then just combine like terms. X squared minus 2x squared is negative 1x squared. 5x and nothing else is still just 5x. And then negative 7 and negative 9 is negative 16. All right, so just combine like terms. How about multiplication? What two methods did we go through? What two methods did we go through? Mike, go ahead.
Box method and like double distributive method.
Good. Box and distributive. Double, triple, whatever the distributive part is. I don't care which one you use. Either one's fine. Let's do an example of this. All right, 2x plus 1 times the quantity x squared minus 3x plus 7. Either use box or double distributive. I'll do both real quick. Check your answer, please. Okay, so double distributive will look like that and like that. So double distributive I'll do first. I'm forgetting my cube part there. Okay, now remember with box method, what's the one thing you want to look for? With box method. It makes it easy to combine like terms at the end. What do you notice about box method?
Diagonally, they're the same.
Yeah, diagonally. Very good, right? All right. These are going to sum together. And these are going to end up summing together. If there are any like terms, obviously, that's where they would be. So I'm not going to combine those because it's the exact same expression you get as an answer. All right, so using box method, you get that. Using double distributive, you get the same thing. As a result, giving you 2x cubed minus 5x squared plus 11x plus 7. Okay? Any questions on that one? The last example, last one. If you recall, we did some examples with exponents as like that. How would I perform this operation or simplify this expression? How would I simplify this one? So we have x to the 2n times the quantity x to the 3n plus 1 minus x to the 4n. How would I go about simplifying this? What operation do you use to start? How would you begin it, Mike? Yeah, distribute. Start by distributing. So this is really x to the 2n times x to the 3n plus 1 minus, again, x to the 2n times x to the 4n. Mike, do the right-hand side first because it's easier. X to the 2n times x to the 4n is how many n's?
6
Yeah. Remembering that we're adding exponents. When you have a common base, you add the exponents. Over here, Paul, what do I get when I add the exponents to each other now?
6
Add the exponents, remember.
5.
Plus. Yep. And that's it. Please, don't try and simplify any further. Nothing else you can do here. Remember, this is like saying the following. If you get an answer at the end, and the answer said this. If you had x to the 8th minus x to the 4th, you can't subtract them. They're not like terms. So please don't try and subtract these two. You're done at that point. You can't go any further. All right? Format for the test. All right? Format. 4 pages total. So it's a shorter test. 3 multiple choice. Well, I'd say 9 multiple choice / matching. And you'll see those two are about 9 of those to start. Then a problem with function evaluation with a few parts to it. A problem with finding domain and range of a function and whether it's a function or not. Another one with just finding the domain with the radical and the denominator stuff. Simplifying like this, using box or double or triple distributive. Difference of 2 squares was one of the rules we did in 4.3. So take a look at those special patterns. And then 2 word problems at the end. Okay, both of which you'll do. 2 word problems at the end. Okay, I expect people to do well tomorrow. Please, study tonight. If you did not turn in your problem set, I expect you to at least email me today. Let me know. They should be done. You had time on Friday.